This is the screencast for section 2.5, example 1, complex zeros and the fundamental theorem of algebra. So last section in 2.4, we found all of the real zeros by using synthetic division and breaking down a polynomial. Well, not all zeros are real. We had a theorem in the last section that said a polynomial of degree n has at most n real zeros, but we saw that it didn't have to have all real zeros. It could have had, so if you had a degree 5 polynomial, it could have had only 3 zeros. Well, now the fundamental theorem of algebra tells us that a polynomial function of degree n has n complex zeros. Complex means both real and non-real, or as you know them, imaginary. And if you remember, imaginary numbers come in the form a plus bi. So we have the a term plus or minus the coefficient of the imaginaries. So some of these zeros may be repeated, as they were when we found real zeros in the last section. A polynomial function of odd degree has to have at least one real zero, and that makes sense because, as we learned in section 2.3, an odd degree polynomial has opposite end behaviors, so no matter what it does in the middle, it has to eventually cross through the x-axis. Then this last piece that we're going to talk about is the linear factorization theorem. Basically, what this says is if you have a polynomial of degree n, which is greater than 0, then f of x has precisely n linear factors. Linear means it would graph to be a line. So for example, if we had a 5th degree polynomial and I broke down and found all of those zeros, real and imaginary, and factored it, I would get x minus the first 0 times x minus the second 0 times x minus the third 0 times x minus the fourth 0 times x minus the fifth 0. It would have 5 of those breakdowns. And each one of these breakdowns, so say 3 was a 0, x minus 3 is a factor, and this is linear. It's x to the first. This individual piece inside the parentheses here would graph to be a line. So in this section, we're going to learn how to combine these ideas and put together some functions, as well as take apart some functions and find out what their zeros are and work on their graphs. Example 1 asks us to combine this idea. So, excuse me, write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of its graph. Okay, so write the polynomial function in standard form. Now, standard form is very boring. Standard is boring. It gives us no information. Factored form already gives us the factors and therefore the zeros. So I can tell you right off the bat that these zeros are positive 2i and negative 2i. Those are the only two zeros. Now, because neither of those are real zeros, the graph will never cross the x-axis. So x-intercepts, there will be none. Now, to write this function in standard form, I am going to have to multiply this all out, which is some lovely algebra, which I know you're extremely excited about. So I'm going to FOIL these together. I get x squared, let's see, minus 2ix plus 2ix would be 0. And then I get minus, so this is negative 2i times plus 2i. So minus 4i squared. And if you remember back in Algebra 2 with zeros, I squared is negative 1. So f of x equals x squared minus 4 times negative 1. So that would be x squared plus 4. Now you cannot check this function by typing into y1 x minus 2i times x plus 2i, because your calculator can't graph using imaginaries. What you can do, though, is check the function you got, x squared plus 4, and make sure it does what you analyzed algebraically that it should do. In this case, this function should not cross the x-axis at all because its only two intercepts are imaginaries. They're not real, so it won't cross through the real x-axis. So let's see if that works. Yeah, it does. Now exercise B. Again, I'm going to start by identifying the zeros of the function. So that includes real and imaginary because it doesn't specify. So my zeros are x equals 5 or 5 comma 0. Then let's see, if this is x minus square root 2i, positive square root 2i, and then negative square root 2i are all zeros. The function will intercept the x-axis though at 5 comma 0, and that's it because the other two zeros are imaginary, so it will only cross the x-axis at 5 comma 0. Next, we need to write this function in standard form. My hint to you, if you want to avoid yourself a lot of work, multiply the I terms together first. I know it's very tempting to take the first two binomials and multiply those together first, but do the I terms first. So I'm going to leave f of x equals, I'm going to leave x minus 5 out here in front, and I'm going to FOIL together the other two terms. So x squared, then I'll have minus square root 2ix plus square root 2ix, which would cancel. And then I have minus, okay, because this is a minus times a positive. Square root 2 times square root 2 is 2. I times I is I squared. I have x minus 5 times x squared, and then remember I squared is negative 1, so this would turn into plus 2. And now I could just FOIL that together, which is a lot easier than it would have been if I would have multiplied x minus 5 times x minus square root 2i first. So now this is x cubed minus 5x squared plus 2x minus 10. That is in standard form. Each exponent of x decreases as I go. I'm going to graph that and make sure that the only place this graph crosses the x-axis is at 5 comma 0. Now as I can see on my graph, the function is still a cubic function. It still has opposite end behaviors. It does a little dippy thing there in the middle, but the only thing, and by dippy thing I mean it changes from increasing to decreasing to increasing, but the only time it crosses the x-axis is here at 5 comma 0. So I've analyzed this function correctly and likely also multiplied it together correctly. Part C becomes a little even more complicated. We have a quartic function. There will be 4 zeros, definitely. So my zeros for this function are, let's see, positive 3 again, so I don't have to list that again, but if it asks me for multiplicities, that would be multiplicity of 2, which means you can expect the graph to do what off the x-axis? That's right, bounce. Good job. So we have positive 3 as a 0, positive I, and negative I. Now I'm going to do two multiplications together at once. I'm going to multiply the non-I terms together and then the I terms together. So f of x equals, this is going to be x squared minus 6x plus 9, which still has to get multiplied by this guy. This is going to be x squared. Now minus ix plus ix would cancel, and then negative I times positive I would be minus I squared, which then that would turn into, since I squared is negative 1, then that would be x squared plus 1. Now I can take each term in this trinomial and multiply it by each term in the binomial, so I'm going to follow my little pattern. X squared times x squared is x to the 4th. X squared times 1 is x squared. Moving on, negative 6x times x squared is negative 6x cubed. Negative 6x times 1 is minus 6x. Moving on again, last term, 9 times x squared is 9x squared. 9 times 1 is 9. Combine my like terms in highest to lowest exponent, so x to the 4th first, minus 6x cubed. My x squareds, I've got 10 of those, so 10x squareds minus 6x plus 9. So that's quite a mess, but hopefully when we graph it, it will only cross the x-axis at 3. It'll actually bounce off the x-axis at 3. It will have the same end behaviors. They will both be pointing up because we have a quartic function, even degree polynomial. So both the left and the right end behaviors will go to positive infinity. So let's see. So after I found a good window with this graph and I look at it, it is still a quartic function. It's got the end behaviors both pointing up to positive infinity. It does bounce off the x-axis at only positive 3, so it only has one real zero, which is positive 3. The other zeros are imaginary. And it looks like my algebra combining all these terms is correct. The now try problem for example 1 is number 1. Write the polynomial in standard form, identify the zeros of the function and the x-intercepts of its graph. So I'm going to do, before I put it into standard form, I'm going to identify the zeros. The zeros of this function are positive 3i, because 3i minus 3i would be 0, and then negative 3i, because negative 3i plus 3i would be 0. Now both of those are imaginary. I don't have any real zeros, so there should be no x-intercepts. Now I'm going to multiply this together. So I'm going to FOIL that out. X squared, and then you have minus 3ix plus 3ix, which would cancel. So minus 3 times 3 is 9, and then I squared. We know that I squared is negative 1, which would change this function to x squared plus 9. Still an equivalent statement, but written differently. Now I graph that to make sure that the function will never cross the x-axis because there are no real zeros, so it shouldn't. And that's true. Plus we have a quadratic, degree 2, and that is like a parabola. Both end behaviors point up to positive infinity.